in this one for you. So thank you. Okay, thanks, Brian. Take it away.
Thanks, Aisha. As Aisha said, my name is Brian Chung. I'm from New York, and I go to school in Boston, and I'm very excited to be here this summer. I worked with Christine Puskis and David Phillips from UNAVCO, and they were just the best mentors ever. I couldn't have asked for a better experience. And my writing mentor is Leslie Butcher. She is from CU Boulder, and she's pursuing a PhD. So I'm going to introduce you to my study area, but first, the title is Prehistoric and Modern Stress Evolution and Seismicity in the Intermountain Region of Idaho in relation to the 1983 Bora Peak earthquake. It's a mouthful, but it's all important. We'll get there. And my study area is in the green box, and to orient yourself just to the pointer. Right there is the Yellowstone hotspot. That's where Yellowstone National Park is, and historically it's moved through this region, and this is our study area. And the next slide is actually a zoomed-in version of that little green box. Okay. So the motivation for this project was the lithospheric complexity of the region. Historically, the Yellowstone hotspot has moved through this area, and in its wake, it left the East Snake River Plain. And it also created an area, an actual arc known as the tectonic parabola of earthquake activity around the East Snake River Plain. So our study area is to the northwest of this region, and the Bora Peak earthquake, as you can see, was right there. And the family of faults we're looking at is in that area. And another motivation for this project is the technique we've been using. It's called Coulomb Modeling, and it's been used in such studied areas as Southern California, China, and Mongolia, and these are very tectonically active areas, so this technique is very important for determining areas of risk. So it has been applied in this region before by Chang et al. And Payne et al., but they were more focused on the Bora Peak earthquake in particular and not the entire stress interaction like we're looking at. And things in this region are actually moving a lot more slowly than places like Southern California, because in Southern California, you're going to have larger earthquakes more frequently. And this region, as you'll see in a second, has very slow slip rates, and the time between earthquakes is on the order of thousands of years. So one more motivation for this project is the Bora Peak earthquake itself. And this is a picture taken earlier this summer. Christine took me on a fantastic field trip, and we got to see everything. So I was really excited to be there. As you can see, the surface manifestation of this earthquake was quite significant. It was well over 6 feet high, and not all earthquakes do that. So this is why it was very interesting for us. And also, this earthquake is the largest earthquake in the historical record of Idaho. So, and that's also significant because it's an interplate earthquake. Normally, the large earthquakes you have are occurring along plate boundaries, but this is the middle of the North American plate. So having such a significant earthquake in this area is quite uncommon. So some fault geography. This is the family of faults we'll be looking at from northwest to south, northeast to southwest. It's the Beaverhead, Lemhi, Lost River, and Sawtooth. The upper 3 faults have been very well studied and are known to segment into 6 subfaults each, which each move independently. So we'll be modeling the activity of those faults individually. And the Sawtooth is a little less well studied and understood, so it's possibly 2 sections, so we accounted for that. But yes, and the dip along the top 3 faults is southwest, so you're going to have the fault planes dipping that way, and for the Sawtooth, they're dipping northeast. And as I said, the slip rates are pretty slow, so we have to look into the seismic record, the paleoseismic record, to determine paleo earthquakes in characterizing the stress of the region. Along the y-axis of these diagrams is the fault itself, so you can see, and the white bars are paleo earthquakes. So you can see that each of these segments correlates directly to a paleo earthquake, and the width is basically a confidence interval of when they think it might have occurred. And since later on, towards 25,000 years ago, things are less well constrained, we began our models at 9,500 years ago, which has some better constraints on these earthquakes. And we've also used the median ages of these, actually the mean ages of these earthquakes in our models for a preliminary model in terms of characterizing the state of stress in the region. And yeah, later on in the future, we'll probably consider the range and its effects on the whole. And this is slip rate data based on the awesome GPS data here at UNAVCO. And you can see that on the y-axis, it's on the order of millimeters a year. And most of these faults are moving less than 0.2 millimeters a year. And the faster faults are closer to 1 millimeter a year. So that's why in the past diagram, you saw the paleo earthquakes are on the order of thousands of years apart. So that's why we have to account for those in determining the state of stress. If we started it now, we wouldn't have a whole lot to go on. So you might remember this picture. This was taken of me earlier this summer. And this picture was actually taken in 1983, just days after the Bora Peak earthquake. So you can see just how fresh the scarp is and how high and significant this event manifested at the surface. And you can also note the effects of weathering and erosion on the fault, and actually overgrowth too. But it's still pretty impressive from what you can see today. It's very remote, so I mean, if you can get there sometime, you should definitely see it. It's very impressive. And also they use scarps and trenching from manual construction in order to determine the paleoseismic record. The paleoseismic record, these brilliant people are able to deduce it based on what they can see in the scarp and the cross-section of this fault. So we're modeling 2 fault planes for each segment, and the lower one is much longer, going down from the brittle ductile boundary to the crust mantle boundary. And this area is in continuous motion, which means it's constantly flowing and accruing stress. The upper plate, the upper region of the crust is brittle, so it occurs in discrete motion, which is from earthquake to earthquake. These are the stress changes are occurring. And in determining the slip that occurs in the ductile section, we account for the slip rate and the time interval in between. So this is a picture of Mount Bora. That's the summit up there. And as you can see, I said it's a very impressive fault scarp. You can see it running along the entire front range of this mountain. And it continues for kilometers, and you can see it from miles away. And Bariontis et al. Studied this earthquake with modern techniques and determined these fault parameters. So that's significant because we don't have these parameters for paleo earthquakes. And we extrapolate these parameters when we're modeling the paleo earthquakes due to similarities in the fault structure throughout the region. And yeah. What we'll be modeling is Coulomb stress change, and that accounts for changes in normal stress, which affects the frictional force along the fault surface, which, if it's higher, it will inhibit motion, and if it's lower, it will be conducive to motion. Also, shear stress change occurs parallel to the fault plane, so obviously a lower shear stress will inhibit motion, whereas a higher shear stress will increase the likelihood of an earthquake. And what we'll be looking for in the following models are Coulomb stress increases and decreases in respectively triggering and suppressing earthquakes. The program we use is called Coulomb, and it's run through MATLAB, and it generates beautiful figures like this. This is just an example, not really relevant to this study. But inputs include the fault geometry and the earthquake parameters such as offset and slip and geography. So it can do a lot in terms of modeling these faults, and it outputs data such as displacement, Coulomb stress change, shear and normal. It also can determine the interactions between all the different fault planes you model. And it'll generate a figure like this. The red, orange, and yellow colors are areas of increased Coulomb stress, which are conducive to earthquakes, and the blue areas are areas of decreased Coulomb stress, which decrease the likelihood of an earthquake. So based on the fault parameters you saw before, this is our model of the Bora Peak earthquake on its own. So you can see that this area of Coulomb stress increase is conducive to all these micro-earthquakes that occurred after the Bora Peak earthquake. And our model will be doing a time-lapse modeling the activity along these other faults and this fault and this fall, and seeing the entire stress field from 9,500 years ago up to the present, including the Bora Peak earthquake. And also, the scale on the right is from -5 bars to +5 bars, and for the rest of the models, that will be what the scale is. So this is the time lapse we developed, and starting at 9,500 years ago, we took each of these snapshots based on when Paleo earthquakes occurred, and in between there's that ductile creep I was talking about, so it also accounts for that. And the black circles represent future sites of earthquakes. So you can see it makes perfect sense that this earthquake occurred right here where this black circle is. And that's generally consistent throughout our models. And keep your eyes on these two black circles, because in the next figure you'll see that those two areas of raised Coulomb stress immediately have Paleo earthquakes. Immediately meaning on the order of thousands of years. So yeah, you can see these two earthquakes occurred right where I said they would. It's not that easy to predict because time intervals are just so long, but still, you can identify the risk areas. And 500 years ago, up to just before the Bora Peak earthquake, you can see right here, this area is significantly increased Coulomb stress, and there's an event waiting to happen there. And it's not that easy to constrain time, but it's easier to constrain. And you can see this is where the Bora Peak earthquake occurred, right where it was probably predicted. And also note the micro-earthquake distribution to the northwest, which is consistent with that initial isolated model of the Bora Peak earthquake. And you can see, including all this other data, it is also in agreement. Also, to the southeast, you have this area of increased Coulomb stress, but there are not a whole lot of Paleo earthquakes there. So that relates to the aseismicity of the Snake River Plain, which is an area of much discussion, but a little out of scope for this project. And up to the northeast, we have these earthquake clusters, which are a little confusing because they're in an area of decreased Coulomb stress, so it's likely that we're not accounting for something in crustal structure there. And again, just to recap, we have that the Paleo earthquakes were consistent with our models. For example, you can see just to the southeast of that earthquake, you immediately have an earthquake on the order of thousands of years. Next, the Bora Peak earthquake was also consistent with our models because this area was extremely increased Coulomb stress. And I know they don't line up exactly, but it was consistent with the model. Also, the northwestern micro-earthquakes were consistent with our model, just as they were for the isolated Bora Peak earthquake, and now it's in a greater context of stress change. And the aseismicity of the Snake River Plain is fully agreed with by this model, but we're not really going to comment on that. And the northeastern micro-earthquakes are a little confusing to us, but we will address those earthquakes in the future. So like I said, in the future, we're going to vary the time intervals in which Paleo earthquakes occurred because they're not very well constrained. So we're going to see how sensitive the field of stress change is and the micro-earthquake distribution is to how we vary those models on the order of thousands of years. And also, slip rates are not that well constrained just because everything's moving so slowly. Even UNAVCO had a hard time using the GPS data to exactly hone in on a specific number for slip rates. And also, we will look more into the history of this region tectonically in the crust, in the intermountain seismic belt, accounting for dikes and faults that might have contributed to those curious northeastern earthquakes. And I would like to thank UNAVCO and RESESS. You guys are awesome. I'm so happy to have met all of you. CU Boulder, NSF, and Christine for taking me on the field trip of a lifetime. She deserves a round of applause just for that because it was 4 days of hundreds of miles of driving, and I will never forget it for the rest of my life. She is awesome. And David also helped organize the field trip, and he's been so supportive of everything we've done. And Susan Schwartz and Erin Todd both are at UC Santa Cruz, and they helped me with the Coulomb modeling a little bit. And Aisha, Peter, Rolf, and Melissa, and everyone. Sorry I forgot everyone, but you guys were amazing. And that's the fault chart.
Very nice job. I had a couple of questions. The first question is, you basically summed all the Coulomb stresses as you move forward in time.
Yes.
Is there any reason to believe that these stresses can be dissipated so that they don't remain constant over 9,000 years?
Well, what we accounted for was the ductile creep and the paleoseismic offsets, but like in terms of what you were saying, certain stress can be relieved based on the activity of another fault, but I'm not sure if exactly they dissipate on their own. Like what we were concentrating on was more the interaction between the stresses rather than how the stress itself may increase or decrease naturally. Does that answer your question? So, like, could you like clarify? Yeah.
Yeah, we can't really say whether there's some other factor going on, but the micro-earthquakes will use orders of magnitude lower energy, so it's probably not going to be from the micro-earthquakes. Otherwise, we don't have any additional mechanisms in place.
And also, like, everything's moving so slowly, so things change on a much larger time scale.
In the last slide, you say for future work, you're going to do micro-earthquakes. You can calculate micro-earthquakes location.
We're going to analyze their location in relation to how the stress field might change based on how we vary parameters.
Just for word advice, there's a nice software package, open source. It's called Earthworm from the ISTI.
Okay.
It's really good for location for microseismic. Even you can calculate real-time data, especially in the U.S.
Yeah, we use the ANSS catalog, so I guess it wasn't as specified as that, but okay, that sounds interesting.
Right. Good job.
Thank you.
All right, let's give Brian another round of.
Oh, wait, we have one more question. Perfectly okay.
Oh, come on, Peter, you've done so much.
So you did a really nice job showing the time varying stress field. But interplate seismicity is sort of a tricksy thing. What in like doing the background work, like what's the deal? Why seismicity in Idaho? What's generating the background stress to begin with?
Well, like initially it was like the lithospheric complexity of the region because we do have the Yellowstone hotspot going there, but also it's in the basin and range, so extension is occurring in this region based on the fact that it's between the Sierra Nevadas and the Rocky Mountains. So it's in a very tectonically interesting area, despite not being exactly on a plate boundary.
Thanks.
Thank you.
Thanks again.